And some of you may actually remember me from my previous talks, Reveal AR Demo Making Off, and what's new in ARKit 1.5.
I'm noticing a theme here, Vlas.
Yeah, maybe. Like there's something, that, with the pattern recognition thing, like it should be dingling right now. Anyway, and tonight I would like to talk about two aspects of some sort of prototypical developer tooling for ARKit apps that I worked on. Actually, it's been some time now. It's started back in last year, but I'll go into it a bit later. Now, you might remember these two blog posts if you have read them. These were published on the Itty Bitty Apps blog, so if you would like to check them out, that's the link. But don't worry, if you have read them, there will be some demos, and I will try to talk through some more details, essentially. So, but first of all, if you're not familiar with ARKit, what is it? So ARKit is Apple's implementation of common augmented reality algorithms and techniques, and augmented reality itself is, well, as per a Wikipedia article, it's an interactive experience of a real-world environment where the objects that reside in the real world are augmented by computer-generated perceptual information. If you translate that to simple English, I probably should have opened that article, it's basically you have your phone, the phone shows, or some other device, am I right? The device shows the camera feed of the real world, and on top of that displays some overlays. And the main idea is that those common algorithms and techniques allow the app to track real world, track the camera location in the real world, and thus position those overlays as if they are in there in the real world. Of course, it's all just, fake. And so, as I said, ARKit is Apple's implementation of those common algorithms. And yeah, the question, I suppose, is why? Why am I here? What am I talking about? The idea to investigate some developer tooling for ARKit, well, third party obviously, came up to Sean, our managing director at Itty Bitty Apps, while him and I were back at WWDC 2018, so last year. So it's clear, and it's becoming increasingly clear, that Apple wants developers to use ARKit in their apps. But some of the tools that are kind of important to support that development are still missing in Xcode or related tools. And for example, that includes things like inspecting and debugging AR sessions, like how we have tools like that for UIKit apps. And so actually visualization, not recording, was the original direction we decided to research first. And Apple obviously have their own internal tooling for that matter, for debugging their algorithms internally and visualizing information that the device and algorithms capture, which helps them make the algorithms robust. But third-party developers like us could also contribute from something similar, even just, for example, having a better, clearer view at the scene comprehension that ARKit builds over time as you scan the environment. And here, for example, it's a screenshot from the Understanding ARKit Tracking and Detection talk from WW 2018. And you can see here on the screenshot how this app has collected the path that the camera was moving in and the raw feature points that the algorithms have detected in the scene. And that's just a feed from the camera with some overlays. And, it's only seemed fitting that, we as creators of Reveal would look into this direction, at least as just a research. And in fact, we actually went with a similar off-device tooling for this direction, for this experiment as well. I personally believe that it could be useful as well to show the debug information right on the device as you use it, but maybe as a mode. And it can also be somewhat a limiting factor because, well, you probably also want to interact with the app and the environment at the same time as debugging the information that your app and ARKit produces. So both approaches are reasonable and useful, but we decided to go with an off-device approach. And so the first question became, okay, we want to inspect, we want to visualize the information in ARKit scene. What can we visualize? Well, there is some information available from ARKit session in form of public API, like from delegate callbacks. For example, session configuration and state, information of frame updates that update up to 60 frames per second, including camera image. Now, that is actually kind of special because camera images are large, and so trying to transfer them in real time from your device to, say, a Mac, that might put quite some pressure on the network, and you might need to actually compress the images significantly. So we actually decided to not try that at all, just to save time. That was a quick experiment. Instead, we looked into capturing the kind of small information, the camera state, the raw feature points. They actually update slightly less frequent than 60 frames per second, which helped. Light estimations, and of course anchors like custom anchors and plain anchors. There are more, didn't do that. There's also world map starting with iOS 11, which could be useful, even if just on demand, like press a button, it downloads the world map, maybe visualizes that. Again, didn't have enough time to do that. So I've started with the very basics, showing a ARKit scene on the Mac that reflects the AR session. What you see here is just kind of the floor. The yellow dots are the raw feature points of the current frame. And this little white pyramid represents the camera. And so these would, of course, update as the data would come from the app. It's using multi-peer connectivity, which was just very convenient because it's available out of the box. And the camera controls, the camera was actually just free because it was using the SyncIt debug camera controls, so you could just move around the scene, look at it. This is actually one of the this is actually one of the first screenshots which I made for this thing. And now, as time went on, it kind of advanced a little bit. So what you see here is, well, an advancement in different directions. First of all, these feature points. So here it's just single frame. Well, what we can do is we can actually accumulate all feature points you get from all the frames. And you can do that pretty effectively because each feature point has a unique identifier, so you can deduplicate more or less. There are caveats, but you can. The other thing you see here is randomly colored plain anchors. And also the points are now not just yellow. They actually use sort of a heat map coloring so that the lower points are, well, maybe inverse heat map rather. Lower points are kind of more reddish and the higher points are bluish. Could have been the other way around, but it doesn't matter. And this is the version of the same screenshot, but without the accumulated feature points. And right there in the corner, well, not the corner, you can see a yellow, now it's yellow pyramid that represents the camera and just one frame. So this is actually a scan of our office at EDBDevs. And you can compare this huge point cloud with just one frame. Now, later, Oliver, our technical director, gave me an idea. What if instead of using those, the color of the point that represents the height, the y coordinate, what if actually we could try and extract the actual color of that point from the camera frames? And so I tried that. So this is a scan of my couch. And at first I tried just monochrome or grayscale because it was easier. Later I've added color. So it's a bit reddish because I usually do this in the evening. So that's the lighting conditions. And there's another couch. You can probably see like a pillow or something. And there's like a picture frame. Now, the way this works, if you're wondering, so this is, again, a screenshot of an app with ARKit session running. And the yellow dots here are these raw feature points that actually, if you just create an AR scene view, you can just specify the debug option and it will just show those yellow points for you. So these yellow points represent the points that AR session has extracted from continuous frames and turned them from their 2D positions on each individual frame to their 3D location in the virtual space. Well, more like real space, right? So what I try to do, and this is maybe not very optimal approach, but it worked, is so I project these points from 3D back to the image space, so I get the pixel coordinates essentially in each individual frame. And then I just sample the image. I did have to downscale the image I sampled first, mostly to reduce noise a little bit because camera frames are actually quite noisy if you looked in the 1:1 resolution. And yeah, that's basically it. It did definitely help that, as I said before, the feature points actually update slightly less often than 60 FPS, more like, I don't know, maybe 10 FPS or something, probably more. And that means that you can easily just compare two arrays of feature points, and if they didn't change, you don't need to sample again. And just doing this on a background thread didn't put a lot of pressure on CPU, so it was efficient. That was another idea that Oliver had. I unfortunately didn't have enough time or brain power to do that, but it's definitely an idea because maybe it's more about time. I don't know. The thing is, he suggested that because he's seen this research that people with, again, much more brain power than I am at Microsoft did like way back. And it was around essentially reconstructing a scene from a series of photos. Like you go to some plaza in Italy, you take like hundreds of photos, and then their magical algorithms will stitch them together, like sort of a kind of panorama, but a bit in 3D essentially. And you can then browse through that space. That was one of the ideas, but again, limitations, both here and time. Anyway, yeah, this screenshot on the side is the representation, the visualized representation of that. You might kind of see colors being similar, I suppose, green on top, blue in the center. Yeah, of course, this is not very precise. Especially because one complicating element there was that camera frames are not RGB. They're YCBCR color space. The Y is essentially luminosity, which made it easier to sample just in grayscale. But converting CBCR and then dealing with the memory layout for those images, it was a bit hard. But it worked out. So as another example, so that's again a photo of our office corner, and that's a scan. Of course, it did take me like a few minutes to actually go around this whole corner and make sure that AR session actually captures all of them. But yeah, as I was doing it, the code was streaming the point clouds back to Mac, so I can then, when I finish, I can browse around the space, look into everything I want. And this is a representation with plane anchors. That, by the way, the green blob is actually a plant wall. That's why it's green. And one other thing I realized would be useful, well, two things actually. First of all is support for camera modes. Essentially, instead of only being able to just fly the space like in an FPS game in God mode, it could be useful to have a bit more constrained modes. For example, first-person mode, where the visualization camera tracks the AR camera. Third-person mode, where it's behind the camera. Top-down mode, where it's always above the camera. And a couple of more free modes like turntable when you're kind of orbiting around the camera, sorry, orbiting around some point which you can then move. And yes, the free God mode. The other useful element was actually iPad support. And that was actually pretty simple because the ARKit code was, it's pretty much cross-platform, just some quirks to deal with. And yeah, just some basic UI for each platform. It's not based on Electron or JavaScript. And the good part about both, when you combine iPad support with camera modes, the cool part is that you can configure your iPad visualizer with, say, third-person mode, have it connect to a phone, which you can do actually without a hotspot because multi-peer connectivity uses AWDL protocol, which is the same as for AirDrop and many other things Apple support. And yeah, that means you can go on site somewhere, open two apps, say one person with the phone for capturing, another person with the iPad, could be the same person of course, and while you scan the thing, at the same time you can also see how it looks on visualization. Now, of course, I can also demo this whole thing while I'm just talking and talking. Okay, so for a demo, I'm gonna need a surface. And of course, we don't have these, I probably used that joke before, we don't have those perfect wooden Apple tables here, but I'm gonna use this beer carton instead. So what will I need for that? I will need to exit this. I will need to run the visualization, visualizer. Well, I will also need to start mirroring my display. That would help. Now I will need to restart this app because of a bug in ARKit, Rata submitted. Okay, so this is like a empty mode. I'm going to use my phone for this. Again, no magic. I didn't connect those things to the same Wi-Fi, so I hope it will actually work. All right, and let's start. Yep, there we go. I'm going to disable the planes for now, just so you can see the points. Okay. Oh, I should probably, sorry, I should probably also start mirroring my display through QuickTime, just so you can actually see what I see here. Okay. Disregard the bouncing balls. I'm gonna show that later. Sorry, what? Sorry, yeah, it's actually part of the second demo. So yeah, as you can see, so the default here is, and by the way, those are you in the background. You can see how I essentially scanned this box. Let's see how that looks in first-person mode. Now, I promise there are no hitches like that usually. It's probably because it's not actually connected to the same Wi-Fi or something else. You can see how there is some lag. I will just attribute that to the way I'm currently presenting things, right? Because otherwise it works perfectly. And yeah, there are some other modes, top-down, which you may have seen. If you've seen the Apple's presentations, you may have seen one of their tools using this top-down mode. I've obviously got very inspired by their presentations to that. So we got the turntable mode. We can just explore. You can see how the bounding box updates dynamically to encompass all the feature points. And in fact, I can actually switch back to the vanilla height-based points, but you know, they're not always very useful, to be honest. Let's see, there are some planes. that ARKit has detected, in fact, quite a few, one for each side. Of course, I can just fly around. It's not very convenient with just using a trackpad. Okay, well, obviously, if I were to move around, maybe scan the whole room, it would be a bit more pretty. Sorry, what? You mean in the yes, actually it kind of does. I used to keep pointing at the screen, and you can see how I'm pointing at the screen. It kind of recognizes dock in here. See this line? I've got to disable the planes. There you go. Again, because ARKit detects feature points or edges or kind of texture, essentially, that's what it sees. It sees those feature points and it gives them to me, and I'm just sampling the image. Sorry? Like, you mean like that? Oh, okay. Well, moving targets in general, ARKit right now is not super good at. It will essentially think that you have more geometry. So if I move this box right now, which I really don't want to do, it will think that, oh, now there is another box here, and the rest is still there. ARKit itself, if I remember correctly, will try and compensate. However, the implementation of feature point accumulation that I have is not as smart, because I simply don't know when ARKit thinks that those points disappeared. It doesn't tell me because they're just mainly used for debugging. What I didn't actually mention is that, of course, it would be very useful to try and extract some private implementation details for this kind of stuff, but it takes a bit more time, and that also means that, well, the implementation wouldn't be as robust. Okay, well, done with this. Let's just stop this and go back to the Prezzo. Put back down. Cool. There is a video, but you can check it out at the blog post. So now that's all cool. That's all great. Of course, the question was how exactly could we maybe commercially apply this. I'm not saying that we would or we can. That's kind of out of the scope. But one interesting aspect from this formula of inspect, modify, debug is actually missing, and that's modification. Now, the thing is, ARKit, in ARKit, most individual objects are actually immutable. So, for example, frames, like the camera configuration, all of the stuff ARKit gives you, or even stuff that you give to ARKit, like custom anchors, they are immutable. Like if you want to move a custom anchor, you need to remove it and then create a new one and add it back. So that means that modification is actually, that'll be very tricky, if not impossible. So we decided not to go in that direction further. However, while sniffing around ARKit's implementation internals in search for some clues, I actually randomly discovered something else, a way to record ARKit sessions. So it actually turned out that using this fairly basic forward declaration of some private APIs on AR configuration, you can run special AR sessions which write sensor data that it captures on a file, or read sensor data from a file instead of hardware. And it turned out really easy to use. There was no need to modify the consumer side of the AR session to make it work. You just specify the right configuration. And I think, well, obviously I can only know from the outside. I think it fits so nicely into ARKit's Intel architecture. Well, First of all, because I hope they're going to actually expose those at some point, but also because of how that architecture is, what this is based on. You can see how, everything starts with hardware. Access to hardware is provided by the low-level frameworks like AV Foundation or Core Motion. And those are wrapped into what ARKit calls sensors internally. And sensors provide some sort of different kinds of data like accelerometer readings, gyroscope readings, so on. And those are used by techniques. And so, yeah, you can configure those techniques, or you can provide configurations that, say, one configuration would kind of tap into the information that sensors read out, and that would save those data on file. Or you can have a configuration that replaces hardware sensors with AR replay sensor, and that reads from a disk. And of course, yes, that includes images in the form of video, accelerometer gyroscope readings, and so on. Cool thing is that this file of a replay is actually a QuickTime movie file, and the extra information like accelerometer readings are synchronized metadata, custom metadata tracks. So in theory, someone could try and extract the information. Well, might be a bit tricky. No. So what they have there is world maps. So they've used those to restore an AR session that you have started previously in more or less the same state as you've left it. So that, or you can use the same mechanism to even try and synchronize two sessions running on separate devices. So this is different because, why is this different? Because a world map is static. The idea for a world map is relocalization, so that you restart a session, a new one, and it knows about the state you've left it with, while the replays are actually a capture of how the scene comprehension actually progressed in time, starting from an empty scene, and as it starts detecting anchors, feature points, and so on. And so once again, the question is why? Why would you want that? Well, I think it actually is pretty much summarized by this DM I got from a certain developer. I decided to hide his identity, just in case. Who reached out to me after we published this recording blog post. So basically what he had to do all the time to develop his app is keep going on site to actually debug the app, which is kind of annoying if you're used to the comfort of your desk or home. While when you have this way to record sessions, you can go there once or every week or so, record your test scenario, essentially, then go back and just keep using one or two sessions to iterate on your approaches, debug your app, and even automate testing. Theoretically, you could use the same approach to, say, run a, I don't know, XCT UI test suite that just starts with a pre-recorded session and checks what happens when user interacts with that scene as the time progresses. So I hope that he's not the only one who actually contributed from this. And of course, I have another demo. In fact, I will try to show how this could be useful. Okay, once again, trusty beer carton. Okay, exit. I'm gonna reset that. And in fact, I'm gonna continue using this thing because I can. But this time showing you the actual phone will be useful. Okay, so let's imagine I have an AR app and I show bouncing balls that are automatically added into the scene when the app detects horizontal or vertical surface. All right. Let's see. Okay, so, oh, there you go. it detected some planes, and it starts showing those bouncing balls. Cool. However, there's just one thing kind of missing here. I don't really like the timing of this bouncing. It's kind of unnatural, but things like that, animation duration and timing, they sometimes take a lot of time to kind of finesse. And I don't want to run the same session all over again. I mean, maybe I don't have a trusty beer carton next to me all the time. So what if I instead use this recording technique? So what I'm going to do is I'm going to stop this. In fact, I'm going to restart the app just to clear its state and reset this. So what I'm going to do instead, I'm going to record a replay. Boop. All right. I'm going to make sure that this replay actually has enough stuff that I need. Like here are 3 planes I would be testing against. And I see enough of the scene maybe. Okay, let's stop this. All right. Should be enough. Now, I'm going to open Xcode. What can go wrong, right? Well, in fact, of course, I have prepared an example of how I might better like the duration and timing function here, and I'm going to run the app again. I know I should be using wireless debugging, but let's just say I don't have enough time. Okay, kind of like how when you're mirroring through QuickTime, it shows 9:41 as the time of it. Okay, and so this time, instead of actually running the session again, I'm going to put the phone down, and I'll just press one button. All right. Yeah, I kind of like this better. You know, it's using the ease out timing and slightly slower animation in general. Okay, I think users are gonna love it and gonna give us 5 stars. Let's ship it. You can also notice that once the actual replay stopped, the session actually keeps running. It just doesn't get more sensor data, which means the scene keeps running. It's just kind of frozen. And I'm pretty sure I can still interact with the scene if I wanted to. I just won't. Instead, I'm going to show you a different example of a replay, which is on my iPad. And once again, by the way, as you can see, the session driven by the replay also streamed its data right here on the visualization side. Okay. Oh, not microphone. No. Okay. Which one? Which one? I think this one. Playing. One interesting aspect is that because of the way it's implemented internally, it actually takes some time to start a long replay, probably because it actually reads lots of data. Interesting. The visualization doesn't connect. All right, let me try that again so that hopefully we have a full picture. Oh, sorry, I totally forgot. This version actually doesn't have the visualization, so I'm going to just, I will simply show you the replay. What I will also show is how I can interact with the session that's driven by the replay dynamically as it goes. So it's not fully pre-recorded. So this is it's a live session. It's not a live recording, of course, but it's a live. Can you just get out? There you go. So what I can do is I can tap on surfaces that are detected to put this box in it. And you can see how this box stays in place because, well, I put it in the live session, even though I'm not in the office and it's definitely not August. Good question. Unfortunately, from my testing, it seems like running a replay session requires some of the same hardware or capabilities as a real session, probably mostly metal support. But I didn't dig too deep. Maybe with some extra convincing, it could still run. So what happens? It just throws kind of the same error as you would happen if you try a real session and simulate it, just like missing hardware, something. Maybe there's just like a hard-coded condition, like if you're on simulator, you cannot run AR sessions. Who knows? I would really love if you could run this in simulator because that's good for automation testing. Yep, so keep putting the red box everywhere. That's the planter, by the way. Of course, yeah. I think we're hiring, maybe. Boop. Well, you can. Good one. I'm pretty sure I was working on this sometimes in my free time, but don't tell anyone. Yeah, oh, there you go. You can actually see the visualizer showing the scan that I've made. Yeah, so that's the demo. Okay, I'm gonna switch back. Probably. Actually, funny thing is, someone asked me, well, us, this question in the, oh, I didn't mention, by the way, if you didn't read the blog post, you might not know. Both of these techniques, the visualizer, that whole thing, and the recording, both of these are open source on GitHub. So just check out the blog post if you want to tinker with those. So yeah, as I was saying, one person actually reached out to me and asked, like, hey, can I actually extract the, I think, EMU or something? Basically, the gyroscope and accelerometer data from it. And I'm like, I have no idea, but I will see. I looked in the hopper, and I think the data is actually encoded in JSON. So you probably can extract that. It's probably going to be like XYZ and time, the timestamp for one reading, and there are like lots of them. But I'm not 100% sure. Maybe there are like some identifiers that you need to guess or extract from ARKit to deal with that. So let's just say it's possible in theory. Okay, that's again, that was my backup video. You can watch it on the blog post. And yes, by the way, I have submitted a radar. You can duplicate that if you want to expose this sort of functionality publicly for development purposes. Its current status is duplicate of an open one, so I guess here's hoping, but you never know what that could mean. And yes, if you want to have a link, it's also in the blog post. Once again, you could just use that link to get to those two blog posts. And that is it. Thank you. Any more questions?
Do we have any questions?
In your early demo of your, I guess, debugger tool, you had all the points. Do you just feed them to SceneKit, or do you have to have a spatial index of them externally? And if you do, what did you use for that?
So that part was actually fairly straightforward, the 3D part of that, the positioning, because SceneKit in each AR frame, which you get updates for, it gives you this, well, actually 2 arrays or 1 array if you're using Swift of those feature points. The feature point itself is represented by a 3D vector and a unique identifier, basically a number. And yeah, that means that as long as you can encode all this information and stream it to wherever you want to visualize that, actually displaying that in a separate SyncIt session should be easy-ish. That was using I think it's called a point cloud or something. There's like a special kind of geometry you can use in SyncIt to just put like point sprites essentially, and even color them with some special custom shader. Anyone else? So the cool thing about, as I mentioned before, of course, you can deduplicate the points by their unique identifier. But even if you have like 10,000, for your GPU, 10,000 points is like nothing. Modern GPUs crunch through that kind of data instantly, well, almost instantly. Because again, it of course depends on you feeding the data in an optimal form. But if it's just 3 coordinate arrays, three coordinate vectors, or 1 vector per point, then yeah, it's pretty optimal. It should be very easy.
With the replay that you were showing, where you recorded a scene and then you were playing it back through the phone, you said that you weren't recording the video stream because it would have been too much?
Well, as in, I wasn't transferring in real time to visualization.
Right, so you recorded it beforehand and then passed it across.
Yeah, I deliberately tried to separate these two aspects because while they kind of help each other, they're actually separate.
Okay.
And the recording itself, it has all the information, full video and the data streams, and it's actually quite heavy, quite large if you record like even 5 minutes of it. But for the streaming components, no, I'm not streaming the images because well, I would need to compress them, and I'm not sure about bandwidth that AWDL for multiplayer connectivity would give me, though it's kind of, should give you at least 2 megabits per second, so yeah.
Mm-hmm. When you were playing it back on the phone, were you streaming the points back, or was it just recalculating new points based on the video that you were sending back?
So the recording that ARKit makes through the private API, it saves that as a video with associated data. And I just give those private APIs the URL essentially for that file. And yeah, it treats the video, treats that as the stream of images from the camera essentially, and reads the metadata. It treats that as data from real hardware. And so, sorry, what was the question again?
So when you were replaying a session
yeah.
in an ARKit session on the phone,
yeah.
Were you streaming back the point cloud data and it wasn't picking back up the old point cloud data, or was it recreating it through the old video stream?
It was, essentially it was getting and streaming the same exact data as it would if that was a live session.
Right.
Because that's, as I mentioned, that's one of the kind of cool parts about this private API, and I will keep saying it's private API, just as a kind of caveat here. One of the cool parts is that from the ARKit session delegate, for example, perspective or observer, nothing's different at all. So you just specify a different configuration, but from his perspective, it's the same thing. And
okay.
So the visualization part acts just as a observer of the session. Nothing fancy there going on, actually.
Mm-hmm. Just one final thing then. When you show your world being recorded in your scene kit on your iPad or on your computer, I may have missed this, but did you show the capability of that scene being restarted and you can continue populating the rest of the sequence? Or is it one session and done?
Well, I thought about exposing a capability, well, different capabilities to mutate the session, including pausing and restarting the session or doing other things. But I decided early on that, actually I'm probably answering the wrong question here. No, I did not have enough time or patience to add the kind of restart button or anything. Though there was this reset, but it really just clears everything off and recreates all the necessary components to listen for a new session. But in terms of mutating the session, there's just this thing I was worried about, and that if my little framework that sits on the side, if in theory that framework could be embedded into other applications, then it would be kind of dangerous to mutate that session on its behalf or behind its back, because then it might not realize that, oh, actually someone stopped this session, or something has just, I don't know, added this anchor, and now I have no idea how to deal with it, because I don't know about this anchor, or I didn't anticipate that the session would get paused. So I decided not to go in that direction.
Okay, no worries.
Thank you.
Cool.
All right, thank you.